Hello students, I hope everyone is doing well. This video is recorded for Monday the 9th. Monday the 9th. So, as I mentioned, over the weekend, you should complete topic number 9 on Math Nation will count as an extra credit towards your grades. Today, lesson is on symmetries of regular polygons. It's very easy, straightforward lesson. This video will be posted as an assignment, and it will say topic 10 video, and the video will be uploaded on Delta Math. You must watch 100% of that video to get credit for it. Once you watch the video and the day end, I will get a link and we'll upload that on Google Classroom. I will teach these lessons using the quizzes.com. So this will work as your Nearpod type of thing, and you will just follow along with the video, submit all your answers, and mark your assignment done. Homework 4, it will be on symmetry, and just submit a screenshot with the smart score and your name on it. Okay, so let's go to the Google Classroom and show you where everything is. So on the side here, you should see week 11, and you probably can see that everything here is still grayed out because it's not sent out to you yet, but it will be on time. So hopefully Sunday night, you will get all of these assignments sent out to you. So this right here, topic 10, is where you click on the link and go over it with me as I'm doing it in the video. And this one is the instructional video. It is on Delta Math. So you just go to deltamath.com. You will see an assignment that says topic 10 video symmetries in polygons. And once you log in. Now, if you forgot your login or you didn't create an account, you still can. That's all okay. You forgot your login, just send me an email. I will do my best to send it back to you. You must complete this assignment at assignment 10 as you are watching the video, which is the quizzes link. Don't forget to mark here done once you watch 100% of the video on Delta Math. The homework that goes along with this will be a skill on IXL on symmetry, and all you need to do is submit a screenshot of your score. You must get an 80% or higher of your score. Okay? So remember, you must be logged in every day to your classes on the Google Meet for the sub to take your attendance. Okay? In case that there is no substitute in the class, I will take your attendance based on you watching Delta Math video. So every video will be due the day of. So it will be assigned in the morning and you will have access to it around 6 a.m. and it will end around midnight that day. So you have the entire day to watch the video and complete the lesson. Okay? All right, so let's get started. So so here's that lesson. So this lesson talks about symmetries in regular polygon. And quickly to remind you what a regular polygon is, regular polygons are polygons that have equal sides and equal angles. All sides are equal and all angles are equal. Okay, so let's talk about symmetries. So a line of symmetry is a line that divides a figure into two mirrored image. A line of symmetry divides the figure into two mirrored image. The rotational symmetry, which something we'll talk about, is when the figure can be mapped onto itself by rotation. And I'll show a quick animation of that. A diagonal of a polygon is any line segment that connects non-consecutive vertices of polygon, which also I will show what each thing mean. So on mathsisfun.com, there is the rotational symmetry, and I think that might be the best way to show it. And I will attach this link on Google Classroom if you would like to play with it. But look at this. You see how the image has been rotated until it flipped back where it was? You know, this can happen multiple times. So what we learn with the rotation symmetry is what is the smallest angle that can rotate a figure onto itself. Look at that. 1, 2. Okay? So that's really what the rotational symmetry is. The regular symmetry, and I think I have something here for it, it says symmetry. So the symmetry is just a line that goes through a figure and exactly in the figure and reflects it onto itself. So if you look at this figure right here on the mountain, you see how it is reflected at the bottom here. So the line of symmetry would be the line that goes down, that really brownish edge that we see, and this image is reflected onto itself right there. That's what a reflection symmetry is. Okay? The diagonal is something that goes through one side to the other, and I will show you how to find diagonals and everything, but this is just a quick way of understanding what symmetry is, especially the rotational symmetry. It is a big deal. We will learn everything about it today. All right, next let's talk about this. Which of the following polygon are symmetrical? Remember, symmetrical means that you split them exactly in two equal halves. Okay, you split them exactly in two equal halves. So let's take a look at this. Which one of these I can split in two equal halves? So remember, diagonal means that it's a line that goes from one vertex to the other. So if I split this that way, do I get the same shape? If I split this that way from one vertex to the other, do I get two of the same shapes? If I split this that way, one vertex to the other, do I get the same shape? And I guess this accidentally came to be the same, but do I get the same shape here? Okay, now so this is called a diagonal. I can see in the first figure that the star is reflected onto itself, so I will pick that because I see that the shape that's on the right is exactly as the same as on the left. We can also do a different line, like a horizontal line. You can also do it this way. Every time you are trying to split that, you'll see that you'll get two exact figure on each side of it. So that is a symmetrical shape. So I'll pick that. Same thing here. This is also a symmetrical shape. Okay, because you can see a triangle and the same triangle right there on the top. You can also see if we do one side, if you do the other side, we will get two other triangles as well. So this is symmetrical. This is also a symmetrical shape. Okay, now I think that this is an error. I just have seen that now, so I'm not going to pick that one as an answer, even though this is the same shape as this, because it shouldn't really be that shape. Okay, I will fix it before the link becomes available for you, so you'll see that this shape will become unsymmetrical. Okay, it will look like an irregular polygon. Okay, all right. Let's take a look at all of this. So consider the following rectangle. Reflect the image across line x equal to -1. Does the transformation result in the original pre-image? Let's take a look. Here's our triangle where x equal to -1 on the x-axis, where -1 is a line. So that's really what x is equal to -1. So just make a big red line here. My question is, this is x equal to -1. Okay, this x is equal to -1. Is this particular problem, like as I am looking at it, does it result in a, let's read the, does it result in the original pre-image? Yes, if this is reflected on that line right there, it will result in a rectangle, the same one. It just goes around in a rectangle. So the answer for this question is yes. Just like I said, this is a very easy lesson to do. So it is yes. All right, same question, but now the line changes. Y equal to -2. So let's see. Y equals, so on the y-axis, where -2 is, I'm going to draw a line, which is this way right here, right? Draw a line. My question, so this is y equal to -2. Does it reflect onto itself? How do I know that? And just to be clear, if you look at the left or the top of the red line that I drew and the bottom of the red line that I drew, if they're exactly the same, then the answer is yes. If somehow the line made the figure not symmetrical, then it is not, it's a no. So let's look at this rectangle. You can see here's 1 unit, 2 unit, 3 units, and then at the bottom is also 3 units. So this also would be a yes. So this figure of that rectangle is the reflection here can happen horizontally and can happen vertically. It would happen horizontally at y equal to -2 and vertically at x equal to -1. Okay? So the answer for this one should be also yes. Oh, it was a no. Oh, it's a yes. I'll fix that one as well. I think this is the one that was no. Y equal to -1. So at y equal to -1, right here, where's -1? Right there. Here's where y equal to -1. We'll just make a horizontal line. Can you see that this line did not split the rectangle into two congruent pieces? So therefore, this is not an original image. Okay, so this is a no. I think might be a bit error on this one. Yeah, so I think the two questions are flipped, so I'm going to fix them, okay? Consider the following rectangle, same one. The two equations that map the rectangle onto itself were, so remember, I know that we kept doing it, but I'm going to draw them again. It right there, and change that color. Oh, let me just write it down for you. So this would be x equal to -1. This would be x equal to -1. And then I'm going to change the color to the y. So it would be at y, where y is equal to -2. So I'm going to draw that line right there. So this would be y equal to -2. Y equal to -2. So this right here, the two lines where the rectangle can be mapped onto itself. So this is what I'm going to write as an answer. X equal to -1 and y equal to -2. When we did y equal to -1, which I can also draw it here, you probably can see that this line right here did not make it symmetrical, or didn't make it exactly, didn't go through the center of it. Okay? All right, let's close that picture and let's write down the answer here. So it was x equal to -1 and y equal to -2. Okay? Let's try one more. It says which line will carry the figure onto itself. And I just put a hint for you. Graph each line. X is 1, Y is 2, X is 2, 4, and 6. Let's see. This is the trapezoid. The first one is X equal to 1, so let's draw that. So X equal to 1, on the X axis, where 1 is, we just make a straight line that goes through that point. So it will be here. Okay, and this is X equal to 1. Then you probably can tell that this does not map it onto itself, because you can see that this right here isn't the same as this part right there. This part on the left is quite smaller. Okay, next one is x equal to 2. So let's move x to 2. So here's where 2 is. X is equal to 2. Okay, the blue line. And I'm going to show all of them at the same time because I really want you to visualize each one. X equal to 2. Are these exactly the same? If you are able to tell, if you can't tell, just count the units on each side. So on this side right here, we have 1, 2, 3, 4, and then on this side we have 1, 2, 3, 4. At the bottom two should be the same units on the left as it is on the right. So x equal to 2 is an answer. It will map that trapezoid onto itself. So I'll pick that one. I didn't want to go through this really that quick. Let me go back very quick. I wanted to show the other lines as well, but the answers are gone. Well, it's okay. But I would actually draw the other two as well and see if it will graph them or not. But anything that's a Y going through or anything, it might be hard to see. Okay? Because it wouldn't map it onto itself for Y. It would only be X. All right, moving on. All right, in a regular enneagon, this is where I'm talking about the diagonals. How can we find diagonals in any polygon? In a regular n-gon, there is two ways. There's a gon that has a odd number of sides, and there's polygons that have even number of sides. So like we can say triangle has odd number of sides. A pentagon, the 5 sides, the heptagon, the 7 sides, and the nonagon also. All of these are odd ends. All ends are odd. If this is the case, then the lines of symmetry, which are the diagonal, will pass through a vertex and a midpoint of the opposite side. To be more specific, here's a vertex, okay? The midpoint will be where that line right there splits in half. So it has to be right the one in front of it. You see where it says here? Opposite. So this is a line of symmetry because it splits it exactly in a half. Okay, now this right here, also that's a second vertex. It will go also here. You can see that every time I'm doing a vertex to a midpoint, I see that the pentagon is split into two congruent pieces. Here's another one as well, right there. Here's another one. Okay, there's also a fourth one. Okay, and there is a fifth one. Okay, so that's if the n is odd, the line of symmetry will pass through vertex and a midpoint of the opposite side. Okay, so let me clear this very quick and show something else. So if I tried vertex to vertex, so let's say if I did vertex to vertex, does it split it in two congruent pieces? No. So that's why when it's odd, it has to go a vertex to a midpoint to get you exactly two pieces on the same side. Okay, so again, when it's odd, your lines of symmetry must be through a vertex and a midpoint. A vertex and a midpoint. All right, what about if it is even? Well, the even, I call it the lucky scenarios because it gets both. So the lines of symmetry can pass through two vertices or a midpoint and an opposite side, or two midpoints. So let's see that. I'm going to try the vertices first. So a vertex to a vertex, they must be opposite from each other. Okay, so here's one. You see that it splits it in half? Take a look. In a half. Also halves. Also halves. Okay, now I've done all the vertices. Now let's try the midpoint to midpoint. Change that color to like reddish. All right, midpoint to midpoint. So from here to here, midpoint still splits it in half. Midpoint to midpoint. Midpoint to midpoint. Midpoint to midpoint. You can, I think that's it because we have 6 sides. Okay, so again, if n is even, which means it's has an even number of sides, so quadrilateral, hexagon, octagon, decagon, what's the 12 gons, 14 gon, anything that has an n that's even, the lines of symmetry will pass through two opposite vertices, and or it can pass through two midpoints. It can pass two midpoint. Okay. All right, let's move on. Pretty easy and straightforward. Let me just clear that, sorry. Name the lines of reflection that will reflect this polygon onto itself. Let's take a look. This is a 1, 2, 3, 4, 5, 6, 7, 8. It's an octagon, which means n is even. So n equal to 8, it is even in this case, which means that your lines of symmetry or lines of reflection will go two ways, midpoint to midpoint or vertex to vertex. Midpoint to midpoint, vertex to vertex. So what I would do is I would take a look at all of these lines drawn. So this line C right here goes exactly through one vertex to a vertex. Does it give you two exact half? It does. So C is a line of reflection. Let's try D. Does D give you, not D, that's A, I apologize, it's A, D is the bottom. A goes through the octagon, however, it's a midpoint to a vertex. midpoint to a vertex. In an even case, it has to be midpoint to midpoint or a vertex to vertex. Okay, so D or line A, it's not an option. So line A can't really work. So let's just put an X on it. But line C perfectly makes it symmetrical. Okay, so let's go back here and pick line C. So reflection across A, no. Reflection across B, well, B doesn't really go through it at all. So B is out. D is also out, which I put C and C twice, so I can't remember which one was the correct answer. I'm going to assume this. Yeah, goes through line C. All right. Next would be the rotational symmetry, which the ones that I showed here. And let me show it to you again. Rotational symmetry means, here, I should share that. Rotational symmetry means a shape has a rotational symmetry when it looks the same after a number of rotation. So here we go. It's a circular move. Okay, let's take a look at that one. Okay, now we are not going to deal with weird shapes like that. We are dealing with polygons since we're learning geometry. So let's read a rotational symmetry. A figure has a rotational symmetry when it rotates the figure around a certain point by less than 360 degrees, and the figure appears to be unchanged, which is the circular move of a polygon. A center of rotation means the point around which the figure is rotated to come back onto itself. An angle of rotation, which is the most important part of this, angle, I meant to say most important, okay? It's the smallest angle needs for a spin, okay? The idea of spinning the polygon to go back to where it was. How do we find it? We use 360 divided by n. Remember, we used this formula before when we did the central angles, which is really the same as an angle of rotation. Rotating a regular n-gon by a multiple of 360 over n carried the n-gon onto itself. You must remember that formula, 360 over n. 360 over n. Okay? All right, let's move on to a few examples. I think this would be our... All right, so let's clean that. It says, what is the smallest angle of rotation that will map a square onto itself? So let me remind you, the angle of rotation is found using the following formula, 360 equal to, so angle of, so angle of rotation is equal to 360, oh, I don't know what happened, but I'm going to go back. It was answered somehow. I think I flipped something by accident. But the angle of rotation is always 360 divided by n. And since it's a square, n in a square means 4 sides. A square is 4 sides. It's not a square. A square is 4 sides. Okay, so to find the angle of rotation in a square, you would divide 360 divided by n, and that would be 360 over 4. And I probably can use this. So it will be 360 over 4, which is 90 in this case, degree. So the smallest angle of rotation would be 90 degrees. Okay, so 90 degree is for one rotation. Okay, one rotation. So every time you eat a 90 degree, then it will be an additional rotation. So if I want to spin that square one more time, then it will be 180 degree. If I want to spin it 3 times, then it becomes 270 degree. Then if I want to spin it 4 times, then it becomes 360 degrees. And I can keep going, keep adding, because you can spin however many times you want. So the 90 really represent the smallest angle of rotation, but it can keep going in the multiple of 90s because I can rotate the figure multiple times. Okay? Let's try a pentagon. What's the smallest angle of rotation that will map a pentagon unto itself? So in a pentagon, to do a pentagon unto itself, pentagon n is 5. So let me just open this. N is 5. The angle of rotation is 360 over 5, or over n, and that would be 72 degrees. Okay, that would be 72 degrees. And again, the multiples of 72 actually would do a multiple rotation. So I can add another 72, so it'll be 134. I can add another rotation to the 70, and those are all angles of rotation. These are all angles of rotation. Okay, let's try one more. 15. Smallest angle of rotation that will carry an octagon unto itself. Octagon n is 8. Okay, so I can erase this. N is 8 and then octagon. So you see how it comes back to something we learned in Polygon? So when you do 360 over 8, it will give you 45 degrees. And again, and it's multiple. So 45 degrees, and it's multiple. It can also be 90. It can be also the one, you can add 45 to 9 will be 135, then it becomes 180, then it becomes 100 and I'm sorry, 200. And so every time you add 45 degree, it'll just give you another angle of rotation. Okay, in this case I only chose 45. I'm focusing on the smallest angle, so the question says smallest angle of rotation. Finally, the smallest angle of rotation when it maps a nonagon unto itself. Nonagon n is 9. Great. So it would be 360 over 9. Sorry, not 8. 360 over 9. And that would be 40 degrees. That would be 40 degrees. And please remember, this is the smallest angle of rotation, but if the questions did not say smallest, it can be 40, it can be 80, and then every time we add 40. So as long as it is a multiple of that smallest angle of rotation. And I think these questions are in your IXL homework. 40. That's it. Okay. So, let me clear out. Once you're done doing this on quizzes, it will grade itself, okay? And you'll be all set. I don't know how many times you can try this particular lesson, okay? But I do know that I'm going to have the link available for one day. The link will be available for one day, but the video, it'll be posted. You can see it at all time, okay? So that's all. Thank you, and have a great Monday.